Hello everyone, welcome to the second lecture on shear force and bending moment. In the previous lecture, we discussed about the effect of external load such as shear force and bending moment in the beam and method to determine the shear force at the section of the beam for the given loading condition. Now the objective of today's session is, after this session, you will able to draw the shear force diagram and bending moment diagram of the beam for the given loading condition. The first thing, what is shear force diagram? A shear force diagram is a diagram which represents the variation of shear force across the length of the beam. Now take an example of beam to understand the method to draw shear force diagram. Consider a cantilever beam loaded with the point load as shown in figure. To draw the shear force diagram, first we have to draw the free body diagram of the beam and then find out the value of reaction forces and reaction moment by using the condition of equilibrium. So first, in cantilever beam, the point A having the fixed support. The point A having the fixed support, so there is a reaction force in vertical direction, in horizontal direction, as well as the reactive moment MA acting in the counterclockwise direction. So we'll find out the value of RAH by using the condition of Fx0, then the value of RAV by using the summation of forces in y direction is 0, and the value of MA, that is 115 Newton meter counterclockwise, by using the condition of equilibrium, that is the summation of moment about any point is 0. Now, to draw the shear force diagram, we will use the method of section. So in the given beam, there are three sections: DB, DC and CA. This is BD, DC and CA. There are three sections in the beam. So we will first consider a section DV. That is, we will draw the shear force variation across the section BD. Right? This is section BD. We will consider a section line XX at a distance of X from end B. At the section line XX, we will consider the right part of the section. Right? So there is only one vertical force, 10 Newton, acting downward. So the value of shear force at section XX is 10 Newton. So we'll find out the value of shear force at salient point of the section BD, that is the value of shear force at point B, that is at x equal to 0. The value of shear force is 10 Newton, and at x equal to 3, that is at point D, the value of shear force is 10 Newton. The variation of shear force, the value of shear force at section XX is 10 Newton, which is independent of x, which represent a line y equal to constant, that is the line having 0 slope, right? That is y equal to constant. So first we plot the or represent the shear force at point B and then at point D. So for that purpose, we have to draw a reference line. This is the reference line for the shear force diagram. This is the value of shear force at point B and at point D. And this equation, SFSX at section XX is 10, which represent the variation of shear force across the section BD is constant, that is independent of x. So we will connect the point D, point B and point D, the value of shear force at point D and D, by a line which is parallel to the reference axis, that is x-axis. Okay. Now next, now consider another section, that is section DC. For that purpose, we will consider a section line xx dash at a distance of x from B. At this section, there is a 2 point forces acting downward. The first one is the 10 Newton and second is the 5 Newton. So the value of shear force at section xx dash is 10 plus 5, that is 15 Newton, which also represent the y equal to constant. That is a line which is parallel to the x-axis, that is slope, the line having slope 0, right? So the value of shear force at salient point of the section DC is, that is at point D, that is we'll put the value x equal to 3, that is 15 Newton, and at point C, that is x equal to 4, the value of shear force is 15 Newton, right? That point D, the value of shear force is 15 Newton, and at point C, the value of shear force is 15 Newton, and the variation is straight line, that is a line having constant, or we can say slope 0, that is parallel to the reference axis. There is a interesting point is here. At point D, there is a sudden variation in the shear force diagram, that is from 10 Newton to 15 Newton. Why it is happening? Because of the point force is acting at point D, and we have already discussed in the previous lecture how to find out the shear force at point D. Because why this is happening? Because we consider a section line just before the point D, then there is only 10 Newton force is acting, right? If we move just beyond point D, if we consider section line just beyond D, then we have to consider 10 Newton as well as the 5 Newton force. So there is a two value of shear force at point D. The first one is the 10 Newton, which is just before the point D, and second is the 15 Newton, which is just after the point D. So we always remember this. In shear force diagram, there is a sudden variation if point load is acting at that point, right? So now third is the section CA. So for this purpose, we have to consider a section XX at a distance of x from B. Similarly, you can find out the shear force equation, the value of shear force at section XX, which is 35 Newton, right? That is 10 Newton plus 5 Newton plus 20 Newton, because all the forces are acting downward. So there is no variation of shear force, value of shear force from point C to A, that is 35 Newton at the point C, and at point A is also 35 Newton, and the variation is represented by a line which is parallel to the reference axis. And one more point is here, there is a sudden variation in shear force value at point C. Why? Because there is a point load is acting at point C, right? So after this, there is a reaction force 35 Newton, so it is a closed one. So this is the shear force diagram, which represents the variation of shear force across the length of the beam. So this is a reference line, so we will draw the shear force diagram, which is positive, right? Now we'll consider one more example to understand the method how to draw shear force diagram. So we'll consider a cantilever beam having uniformly distributed load of intensity 5 Newton meter. The load is distributed across the length of the beam. The length of the beam is 6 meter. So this beam having one section BA. So for this purpose, we will apply the section method. For this, we will consider a section line XX at a distance of x from B. Now consider this part, right? So the value of shear force at section XX will be 5, that is the intensity of the load, and the load distributed to the length. So UDL load is distributed over the length x. So the value of vertical forces, the sum of all the vertical forces, right, is 5 into x. So this is the value of shear force, which is the equation of a line y equal to mx. That is the line having slope 5. So we'll find out the value of shear force at different points of the beam by putting the value of x. So first we'll put the value of x to find out the value of shear force at point B. So the value of shear force at point B is 0. Now next, at midpoint of the beam, we'll put the value of x equal to 3. That will give the value of shear force at midpoint, that is 15 Newton. And the last, at point A, we'll put the value of x equal to 6. That will give the value of shear force at point A is 30 Newton, right? So we'll plot the value at different points. At point B, it is 0. This is the reference line. At point x equal to 3, that is at the midpoint of the beam, it is 15 Newton. And at the fixed support, the value of shear force is 30 Newton. So now, how to connect these 3 points? It is given by a equation SF equal to 5x. So the line having slope 5, right? So we'll connect this line by these 3 points by a line, inclined line having slope 5, right? And after this, there is a reaction force, right? And this is the reference line. So this is the shear force diagram for a cantilever beam loaded with a point.